Hey everybody, happy Friday. Hope that you are having a good day. We are going to finish up one small section of your notes today, and then you are going to do some practice for me before I come back on Monday and we finish up the last two topics associated with the measurements unit. So last week you all measured the thickness of aluminum foil, and you told me that if we have a piece of aluminum foil, that aluminum foil has a specific thickness. Maybe we can't measure it all that well, but we know that if we want to calculate the volume of that rectangular solid, it's the length, the width, and the height. And we talked about if you have a cylinder, that we can measure the volume of that cylinder as pi r squared h. And there are a lot of other different equations for calculating volume that we can use for any kind of solid that's a regularly shaped solid. Now, if that's true, then we're going to typically measure that, at least for us right now in our sizes, with centimeters. And so I've got an example for you. It says if a stainless steel rectangular solid measures 5.55 centimeters long, 3.75 centimeters wide, and 2.25 centimeters thick, what's the volume in cubic centimeters? So if we say that volume is equal to length times width times height, and we plug those numbers into our problem, we've got three significant figures for your first measurement, 3 significant figures for your second measurement, 3 significant figures for your third measurement. And so our answer is also going to have 3 significant figures. Let me check with my calculator really quickly. 5.55 times 3.75 times 2.25 gives me a number of 46.828125. 3 significant figures then to round that off becomes 46.8, and my units are cubic centimeters. So that kind of calculation is a calculation that you guys have known how to do all along. It's the calculations for solids that are not regularly shaped that we may have a little more trouble with. So let's talk about what happens when you have a solid that you don't have 3 really nice sides to be able to measure. So let's suppose that we have an object that is an irregularly shaped object. I don't know what that is, but it definitely doesn't have a regular shape. It doesn't have 3 good sides that we can measure, and so we still need to know the volume of that. So I want you to think back to the Greek mathematician Archimedes. And Archimedes is the guy who figured out how to measure the volume of the king's golden crown. You remember that he dropped the crown into a tub of water, and the water level rose. And the water level rose an equivalent of the amount of space that the irregularly shaped solid took up. Okay? So we call that volume by displacement. And if I have that irregularly shaped solid, let me put another little crazy one there in my container, we know that that water volume level in that tank is going to go up. And the difference between those two measurements of volume are equal to the volume of the irregularly shaped object. So when that happens, I can calculate my volume of my object, we'll call that V object, as being equal to the final volume minus the initial volume. And we'll read those using something like a graduated cylinder or maybe a beaker that gives us some specific measurements that we can work with. Okay? So we've got an example that says a quartz stone weighing 30.475 grams is carefully placed into a graduated cylinder. if the water level increases from 25 milliliters to 36.5 milliliters, what's the volume of the quartz stone? Well, when you start looking at a problem like this, I want you to start thinking about which numbers you need, what things are important, what are not. We're being asked to find the volume. And I know that my water level started out at 25 milliliters and increased to 36.5 milliliters. I absolutely, at this point, do not care anything about the mass of that quartz stone. So I actually don't even need that number of 30.475. What I do need to know is the difference between 36.5 milliliters and 25 milliliters. And we know that the answer to that, if we check our math, is 16.5 milliliters. Now that question now is, do we have the correct number of significant figures? So remember when we're adding and subtracting that it's the least number of decimal places. So you have one decimal place here, one decimal place there. That means you have to have one decimal place in your answer. And so the correct answer for this is 16.5 milliliters. One of the things that you have to be able to do when we talk about volumes is to be able to manipulate those as conversion units. So this is a problem that you'll see again on your test. I can promise that you'll have to do something like this. And this example says, given that an automobile has a volume displacement of 498 cubic centimeters in each cylinder, express the volume in cubic inches. So what I know is that I have a cylinder, and that cylinder has a specific area of its base and it has a specific height. And that total volume is 498 cubic centimeters. The other thing that I know is that 1 inch is equal to 2.54 centimeters. So if I want to calculate the volume for this cylinder in inches, I'm going to have to do a conversion. Okay? And this is what I'm going to do. I'm going to set this up as 498 cubic centimeters. And then I'm going to set up my conversion. And I know that I need inches cubed. Same thing we've been doing all along. I've got a starting point. I've got an ending point. I've got a fraction that I'm going to use a unit conversion for to solve this problem. Okay? So if you'll look, I've got centimeters here and 2.54. So I'm going to pull those down to this bottom spot. I've got 2.54 centimeters as the bottom half of my conversion. And then I've got 1 inch. Whoops, didn't want to do that. I wanted that to be blue, but it's not. So circle it again. Okay, there we go. I've got 1 inch, and I want that to go on the top part of my conversion. Again, I'm not changing colors very well. There we go. 1 inch on the top. And now I've got a set of steps to follow so that I can get to inches cubed. But remember that units have to cancel from here to here. And right now I've got centimeters cubed and centimeters. Those things don't cancel. So what I'm going to have to do now is fix that. So here's what I'm going to say. This is the logic that I'm going to use. What I'm going to say is I need for these units to be centimeters cubed. So I'm just going to cube the centimeters. But mathematically, if I make one change to part of the problem or part of the equality, I have to do that to every part. So if I cube the centimeters, I'm also going to cube the 2.54. If I cube the 2.54 and the centimeters, that means I also have to cube the inches and I have to cube the 1. Okay? In other words, what I'm really doing is this. 498 cubic centimeters. I'm saying that 1 inch is the same as 2.54 centimeters. And another inch is the same as 2.54 centimeters. And a third time, 1 inch. That should be a times 1 inch is 2.54 centimeters. And now I have centimeters, centimeters, centimeters. Those are centimeters cubed, and there are centimeters. And I have inches, inches, and inches. That's going to give me inches cubed, which is what my answer should be. And so now what I'm going to do is divide 498 by 2.54 cubed, which means I have to be able to use my calculator. And you can't see me, but I can't use it. I've already had to clear it out. 498 divided by 2.54 cubed, and I get 30.38982456, which is a big long number. But I've got 3 significant figures at my start. Even though I've done a lot of math all the way through there, I've got 3 significant figures as my end, and I'm going to have an answer of 30.4 inches cubed. Okay? I promise that you will see a question like that again. I'd say maybe on a test on Wednesday, but I'll give you a couple of chances to practice that between now and then. Okay? Let's talk about one more thing, and that's density. And let's talk about how we can use these calculations for volume to help us with those density calculations. All right, we've kind of talked a little bit about density before now. We talk about density, typically we tend to think about how heavy things are, and that's the way we make the comparison. So suppose that you have 2 blocks. One is a block of styrofoam, and that block of styrofoam has a mass that's 1 kilogram, which you now know is about 2 pounds. And we're going to hold that in one hand, and in your other hand we've got a block of lead that's also 1 kilogram. They have the same mass, but the lead is much more dense. So when you hold those things in your hands, let's draw a little person with some arms and some legs and a great big hand. That makes me happy. So, okay, there we go. Our little guy is holding a block of lead in one hand and a block of styrofoam in the other. And if you asked him, or I asked you what that feels like, you would say the lead is heavier. Even though they have exactly the same mass. And the reason that it feels like it's heavier, the reason we use that term, is because the lead is so much more dense, it doesn't take nearly as much space for that same mass. So density concept was developed by measuring water. And you're going to find that we use water as an example for a lot of things. We use water to describe a lot of properties and a lot of behaviors. And so here's what we know. Strangely enough, if we have a cube that is exactly 1 centimeter on every side, so that its volume is 1 cubic centimeter, we know that that cube will hold exactly 1 milliliter of water. And if we take the mass of that water, we'll find that 1 milliliter of water has a mass of 1 gram. And so, because density is an intensive property, that means that it doesn't depend upon the amount. No matter how much water I have, It's going to continue to take up more space, but it's still going to continue to take up or have more mass. That's kind of hard to think about, but what I mean is if I have 50 milliliters of water, then it's also going to have 50 grams, and it'll take up a specific amount of space. And then that space is a ratio value. It's proportional, I guess, is a better way to say it. We end up with 100 grams of water, and it's going to take up 100 cubic centimeters of space. And we have 1,000 grams of water, and it's going to take up 1,000 cubic centimeters of space. And so the density is an intensive property. It's not going to change no matter how much you have of a substance. Okay? Density is the ratio value between the mass and the volume. And so our equation is that density is equal to the ratio of the mass of an object compared to its volume. And the equation is D is equal to M over V. Now if you'll look up above the whiteboard, there's a triangle up there. And that triangle looks like this. There's a horizontal line and a vertical line. In the bottom left corner is the D. In the top part of the triangle is the M. And the bottom right is the V. We call this the density triangle, and it works for any kind of three variable equation. But if I want to solve for the volume of an object and I know the density equation, then I can find the volume by looking at this triangle. So here's what you do. If you've got a density triangle where you can see it, you cover up the unit or the variable that you're solving for. So in this case, I would cover up the density. The density is the mass. The horizontal line is a dividing line, and the vertical line is a multiplying line, and I've got D is equal to M over V. Okay? If I want to solve for the volume, I cover up the volume, and what's left over are the mass and the density. There's the dividing line between them, so volume is equal to the mass divided by the density. And then the same thing, if I want to solve for the mass, cover up the mass, and mass is equal to density. There's a vertical line between those two. It's density times volume. And that triangle stays up on the board all the time. And so if you can't remember the density equation, it's up there for you to use as a reference. Okay? So let's look at some examples. Example 1 says, if a platinum nugget has a mass of 214.5 grams and a volume of 10 cubic centimeters, what is the density of the metal? And so I know, and you're going to see me work these problems the same way over and over again. I know that I've got a mass of 214.50 grams, and I have a volume of 10 cubic centimeters. So to solve for density, I'm going to say the density is equal to the mass divided by the volume. So 214.50 grams divided by 10 cubic centimeters. And without even checking my calculator, I know that 214.5 divided by 10 is 24.450. But let's talk about significant figures. For your mass, I have 5 sig figs. And for my volume, I have 3. And so my answer has to have 3 significant figures. And so I'm going to have an answer that is 21.5. Now my units are grams per cubic centimeter. And that's my answer. So what that says is for every cubic centimeter of platinum, I'm going to have a mass of 21.5 grams. Okay? So think about the size of a centimeter. 21.5 grams is about the mass of 4 nickels. Okay? For solids, we generally report density in grams per cubic centimeter. For liquids, though, we typically use grams per milliliter. And when we talk about gases, we measure that volume in grams per liter. And that's because a really small amount of gas takes up a huge amount of space. So we report those density values for gases just a little bit differently. Okay? So let's look at another one. This example says a 1-inch cube of copper, it should just say copper, not coppers, measures 2.54 centimeters on a side. What's the mass of the copper cube given that the density of copper is 8.96 grams per cubic centimeter? So I'm going to write that triangle for myself so I've got that reference. And now I'm going to look at what I've got in terms of information. I've got that the density is 8.96 grams per cubic centimeter. And I don't have a volume and I don't have a mass. So I'm going to have to figure out what I need to do with that. I do know what the shape of the copper is. I know that the copper is in the shape of a cube. And it tells me that that cube, that does not look like a cube, let me fix that. That cube is 1 inch on each side. Well, I'm not going to use inches. I don't like inches. Instead, I'm going to use centimeters. So I've got a volume that's length times width times height, or length times length times length, because those values are all the same. So I've got a volume that is 2.54 centimeters, and I'm going to take or raise that to the third power. Okay? I'm actually not going to do the math yet, just because I know that I'm going to have to do some more math besides this. So the problem asks me to solve for the mass. So what I'm going to do is kind of color over that mass so that I can see what's left over. And if I cover up the mass, then I've got density and volume left. And the mass is the density times the volume. So if I plug numbers in, I know my density is 8.96 grams per cubic centimeter, and my volume is 2.54 centimeters cubed. And if I can find my calculator and do the math, I end up with 2.54 cubed times 8.96, and I get a mass of 146.8280934, and that's way too many numbers. So if you look at your mass, that has 3 significant figures, and your volume will have to have 3 significant figures. No, wait a minute, I said that wrong. Your density has 3 significant figures, and your volume will have to have 3 significant figures, so your mass will have to have 3 significant figures. 146.8280934 is going to round to 147 grams. The nice thing about density problems is that they're mostly plug the numbers into the equation and solve for the variable you don't know. And it doesn't get much more complicated than what we've looked at today. Okay, so you guys work some practice problems, and I will see you on Monday.